Hello, my name is Orhan Yapici and I'm a PhD researcher in University of Birmingham. And today I will talk about the behavior of ferritic stainless steel bolted T-stubs under tension, the second and complementary study of my companion paper on experimental research. This is the numerical investigation. I will make a quick introduction and I will talk about the development of the finite element model which we used in our numerical study, and I will present the results and discussions, and I will talk about evaluation of European standard design provisions, and I will end my presentation with the conclusions. To define the scope of this study, as we know that research on stainless steel structures has mainly focused on the structural behavior and design of individual members, and whilst the response of stainless steel connections has received less attention so far. The European standard, which was developed for the design of carbon steel joints, it's also currently applicable to the stainless steel joints in spite of essential mechanical differences, such as stainless steels have no sharp yield point and no yield plateau, and they have significant ductility and strain hardening. And these differences and the assumption of elastic perfected plastic material cause overly conservative ultimate resistance predictions for stainless steel cross sections. In the scope of this study, we just focused on the connection design, and also the state-of-art studies on stainless steel connections has been reported using full-scale experiments by Elfala et al. And also they also considered austenitic and duplex stainless steel. And after that, the tests on the idealized and isolated bolted T-stubs using austenitic and duplex stainless steel is published by Yuan et al. And also in the companion paper, the ferritic stainless steel bolted T-stub have been investigated by experimental tests. In this paper, the finite element model has been developed and validated against the available experimental test results of ferritic stainless steel in the companion paper. So, if we summarize the numerical study, this numerical study is based on the development and validation of advanced finite element model that can predict the overall behavior and failure modes of ferritic stainless steel T-stubs subjected to monotonic tension. Key simulation strategies regarding the modeling of bolt geometry and overcoming numerical instabilities are discussed, and also the effect of allowing for anisotropy into the finite element simulation is investigated and modeling recommendations have been made. And also the stress distribution through the plate thickness at various locations and T-stubs have been reported, thus revealing both flexural and the membrane component of the load transfer mechanism. And also the numerical results were validated against the experimental results reported in the companion paper in terms of plastic resistance and ultimate resistance, ductility, and obtained failure modes. The assumptions that we used in the development of the finite element model, that we used the Abacus software to create the finite element model. All parts were discretized with the 8-node linear break elements with reduced integration. Also, at least 3 elements through the flange thickness have been carried out to accurately capture the out-of-plane flexion and avoid the effect of shear locking. A more fine mesh was adopted around the smaller area of the bolt in order to more accurately simulate the interface bolt T-stub interface and capture contact. And also surface-to-surface contact with finite sliding was assumed for all contact surfaces, namely bolt shank to bolt hole and etc. And also the penalty friction method is adopted to simulate the tangential behavior, whilst the hard contact is assumed for the normal behavior. And due to the symmetric conditions, only the quarter of the model was simulated, and a quasi-static explicit dynamic analysis was employed. And for the bolts, a cylindrical surface with effective diameter has been used. Also, the bolt heads and nuts were developed as cylindrical instead of hexagonal discs. For the material modeling and anisotropy, the nonlinear material properties of the stainless steel T-stubs and bolts were modeled using the three-stage Ramberg-Osgood model, and the material properties are adopted from the companion paper. Also, the standard von Mises yield criterion with isotropic hardening is conventionally employed to simulate the plastic behavior of metals when they can be considered isotropic. Material anisotropy included in the finite element models because of the multi-axial stress state of material requires incorporating anisotropy during the bending and under extreme deformation. Also, anisotropic yielding was accounted for by means of Hill's criterion, which is built-in feature of Abacus. The coefficients are calculated based on the data that is given in the companion paper. And also for the fracture of the plate, an indirect definition of fracture based on strains values was successfully employed, that in which the fracture was not explicitly modeled but was indirectly defined based on the longitudinal plastic strained fracture. The numerical models were validated using the experimental force displacement curve. It can be concluded that the anisotropic finite element models significantly improve the accuracy. And also S1, S2, D2, and D3 specimens with respect to the experimental response. The load displacement curve is very good, and these four force displacement curves are representative curves. For the rest of the specimens, it seems the model employing isotropic material response with longitudinal material properties display the closest agreement with the test results. In all cases, the T-stubs failed in mode 1 with the formation of four yield lines and significant plastic deformation. In the failure modes shown, the fractional deformation of the flanges are not pronounced since the photos were taken at the end of the test, and the membrane action developed in the T-stub flanges dominates the observed plastic deformation. So if we consider the plastic and ultimate force predictions, it can be concluded that accounting for the material anisotropy when modeling ferritic stainless steel T-stubs is necessary to obtain accurate finite element predictions of the structural response, especially for plastic resistance. If the data on the material anisotropy are not available, the longitudinal material properties should be adopted to ensure conservative capacity predictions. And the accounting for material anisotropy provides some accuracy. This is expected since the vicinity of the holes, these T-stubs are subjected to a multi-axial stress state, so the behavior of the material in all directions needs to be considered by the numerical model. So if we have a close-up of the failure modes of the specimen S1, D3, and D5, this specimen S1 is ultimately failed by the bearing of the T-stub flange, which is accurately simulated by the finite element models, and also D3 was failed with the initiation of crack is clearly seen at the bolt hole, and also D5 is ultimately failed by the fracture of the flange plate between the bolt holes. And all the failure types were accurately predicted by the developed finite element models, where the locations of the accumulation of plastic strain coincides with the location where the cracks were observed during the tests. Studies into quantifying fracture characteristics for ferritic stainless steels and stainless steel balls are currently underway to allow plate fracture to be explicitly modeled. If we focus on the stress distribution through the flange thickness, for flange thickness, the stress distributions at three different locations, middle, end, and location of the bolt, which is clearly seen in the figures, and at the two different load levels, plastic force and ultimate forces, were extracted. For materials with a well-defined yield plateau, such as carbon steel, such an assumption is reasonable. Whilst for stainless steel, which exhibit a gradual loss of stiffness and significant strain hardening, the validity of this assumption is questionable. Hence, it is of interest to determine the actual stress distribution through the thickness at the load level consistent with the plastic resistance of the T-stub. The stress distributions in all locations are symmetric with equal and opposite stress values occurring at the top and bottom nodes of the T-stub, thus confirming that the main load carrying mechanism up to the attainment of the plastic resistance of the section is bending. For all models, the attainment of the plastic resistance, the maximum recording stress is approximately 25% larger of the yield stress. This value was found as much as 2 times bigger in the recent study by Yuan et al. For austenitic and duplex stainless steel, which is related to higher strain hardening characteristic when compared to ferritic stainless steel. So if we focus on the stress distributions at the attainment of the ultimate force, as you can see that the stress distributions shift to the right and a clear asymmetry emerges in all cases. The T-stubs are no longer working predominantly in flexure. They are carrying simultaneously bending moment and tension due to the membrane action. Hence, the neutral axis of the sections can be seen to have moved towards the bottom, and which means compression side of the T-stubs. If we evaluate the Eurocode predictions with the developed finite element model predictions, the predictions from the generated finite element model in which the anisotropic actions were taken into account agree well with the predictions based on Eurocode, considering the nominal yield strength on the longitudinal and diagonal directions. However, assuming the transverse nominal yield strength for the calculation of plastic resistance based on Eurocode causes over-prediction of the plastic forces. As expected, the best agreement is obtained somewhere between longitudinal and the transverse material response with the proposed finite element model. To conclude, a comprehensive numerical study on the structural behavior of stainless steel T-stubs fabricated from ferritic stainless steel grade is reported herein. The material anisotropy included into the developed finite element models, and which employs a quasi-static explicit dynamic solution scheme to overcome the convergence difficulties. The developed finite element model was validated by comparing the numerical to the experimental results in terms of plastic resistance and ultimate resistance, as well as the overall load deformation response. The failure modes of the T-stub were simulated accurately by the developed finite element model. The effect of incorporating the material anisotropy into the finite element model was studied, and it was concluded that the plastic force predictions are very accurate and more consistent when the material anisotropy is considered. Based on the validated model, the stress distribution through the thickness of the flanges at various locations along the length of the T-stub were obtained at load levels corresponding to the plastic and the ultimate resistance of the T-stubs. The observations made in the companion paper regarding the prevailing load transfer mechanism changing from flexural to membrane at high deformations was confirmed. The actual stress values at which the plastic resistance load is reached were found to be close to the ultimate tensile stress at the extreme fibers of the T-stub. It is thus believed that the main source of overstrength observed for the T-stub is not the strain hardening at the developed yield lines, but the membrane actions and also the contribution of strain hardening occurring at high deformation values. This significant reserve capacity can be used to enhance the robustness of the structures. And thank you very much for listening, and I will be here for answering potential questions. Thank you.